Hey guys, so in this video I would like to review, or not review, but look more into, right, go back through the infinite square well and look more at the solutions and more things we can do with those solutions. And the first thing I want to say in this video is there will be a lot of like calculations, integrals to evaluate in this video, and I just want you guys to know I'm going to sort of write down what integral you would do and then do the integral. And and so if you want to go back and do it and derive it yourself, you can, but for the interest of time I'm not going to do the algebra steps and all of the math steps because there's a lot and that would take up a lot of time, and right now that's not where I want this video to focus. I want you to understand the process of how this works. Okay, so we have our potential, right, which is this infinite potential well. We have from x equals 0 to x equals a. We have the particle trapped. It can move freely inside this well with zero potential. But we have these regions with infinite potential that basically says that this particle cannot be there, right? And we can look at, right, we wrote the wave function, psi n equals root 2 over a, sine of n pi over ax. And you may notice that this, right, we actually did use the letter k. This is in the form sine of kx, which is the familiar waveform that we're used to. And that might make you think this could be a state with a definite value of momentum, right? Because we know, because P equals h bar k, right? And so since P equals h bar k, where k is the wave number, this is a wave. It looks like it has a definite wave number. Maybe this is a state with a definite momentum. And so how might we be able to figure this out? Well, there in fact is an easy way, right? Because we know we're looking if it's a state with a definite momentum, a momentum eigenfunction, right? Which means we know how it will behave if we act on it with the momentum operator, right? So let's try that out. P hat acting on our psi n, right? And if it is indeed a momentum eigenfunction, right, and hopefully you can see the t part won't matter, and I'll include it in for our next bit, but for right now, the t part won't matter with this at all, right? For right now, with p hat psi n, right, what we're looking for, if it is a momentum eigenfunction, if it has a definite momentum, we will get some constant, a constant multiple of the of psi n, right? So let's see what happens. Well, if I plug in what this is negative I h bar d by dx root 2 over a sine n pi over a x, right? And if we do this derivative, what we will end up getting is negative I h bar root 2 over a times, and we use just the chain rule, n pi over a cosine of n pi over a x, right? And as you can see, this is not a constant multiple of psi n, right? We have a different function. We have a sine here, we have a cosine here. So they're not constant multiples. So we know that this function, even though it might look like it could be, does not have a definite value of momentum. However, it is true, right? And you can show this using Euler's formula, the e to the I kx equals sine of k, or cosine of kx plus I sine kx. Using that, right, you can show, and I mentioned this for cosine in the other video, that we can show that sine of kx is equal to, let's see, it's 1 over 2i e to the I kx minus e to the minus I kx, right? And if you rewrite this a little bit with our k value for this quantum problem. We can rewrite k, right, as n pi over a. And so this is sine of n pi over a, right? X is at 1 over 2i e to the I n pi over a x minus e to the I n pi over a x. And what you may notice is this right here is a wave function with momentum p equals h bar n pi over a. Right? P equals h bar n pi over a. That's our k value, n pi over a. Right? And h bar k is momentum. And this wave function, this function here, this is a superposition of these two functions. This has a momentum p equals negative, right? Negative h bar n pi over a. Right? One's traveling in the positive direction, one's traveling in the other direction. And what you'll notice is there's no coefficient, right? There's no weighted coefficients here, right? So because of how we know superpositions work, it appears as though this wave function has a 50% chance of having this positive momentum and a 50% chance of having this negative momentum, right? Which is kind of interesting. So it looks like a wave function with the definite momentum, but it's not. It has a definite magnitude of its momentum, right? But it has a 50% chance of going to the positive direction, which is to the right. 50% chance goes to the left, right? And so actually if you average out its momentum, it actually looks like it would have 0 average momentum, right? Not momentum squared, but we'll see that in a minute. So this is a superposition, right? Our stationary states have one of two momenta, and you can show this too if you plug our wave function into the Fourier transform. What you'll end up getting is two Dirac deltas, actually one at this positive momentum, one at this negative momentum. But you can do that on your own if you so choose. Okay, I'm going to get rid of this, and so if you don't have it down, make sure go back and get that down. And I'm going to erase some of this and go on to our next thing, which is I want to talk a little bit about our stationary states. And just to keep full generality, I'm going to make these our time-dependent functions. I'm just going to use omega because the value won't matter that much, so e to the minus I omega t. Right? I just want to show you it won't actually matter for these equations if you use the little psi or the capital psi, but just for good practice, just to make sure you guys know it works with the general solution with the time part, I'm going to include it. But hopefully you might see why it doesn't actually matter, because it will, get canceled out pretty fast. Right, and what I want to do is I want to check the uncertainty principle for these states, and along the way, as you know, to check the uncertainty principle, we have to find the expectation value of position squared, of momentum, and of momentum squared. Right, and so for these especially, I'm just going to sort of write down the equation we would use, and then give you the answer. So we want the expectation value of position, and of course, feel free to do these on your own. So we're integrating over all values of x, but remember the only values of x we care about are from 0 to a, right? Because this function is 0 everywhere else, so if we're integrating it, we're just, 0 area. Okay, and now we have psi n star x psi n, and I just wrote it this way because when we have derivatives, the order will matter. But right now, this is just like x times psi n norm squared, right? Which will help you show, because we're taking the norm squared, the t part we get rid of it, so this obviously will not depend on t, right? Dx. It may depend on t if we have, if it's like a superposition as you saw, but for the stationary states, they're not moving, how could the position or the momentum depend on time, right? The wave function is not is not the probability density is not all changing in time. The wave function is, but and so if we do this, we plug this thing in, what we would get is we would get a over 2, which actually makes a lot of sense, right? If the particle can be anywhere between 0 and a, right? Where on average would it be? Sort of by symmetry, you would think, right? Unless you have some weird oscillation going on, which we have with the superposition states, you would think that the wave function would end up right around the middle, right around a over 2, right? And so that's right, or at least on average. Okay, if we look at x squared, right, which is, remember this is x hat, but x hat is just the variable x. So this is 0 to a, psi n star x squared psi n dx. Even more room because this one's a bit longer. This one is 2 pi squared n squared, right? 2 pi squared n squared minus 3 over, all over, 6 pi squared n squared. And then all of that times a squared. Okay, momentum. And if you remember, this will also show why the time part won't matter. This momentum operator, I'll write it out, just the operator. So psi n star, times minus I h bar d by dx psi n. Right? And when we do this time part, right, will be treated like a constant, so it comes out of the partial derivative, and then when you multiply it by the e to the plus I omega t from the complex conjugate, it cancels out to be 1. Right? And same thing when we take the second derivative in the next part. Dx, right, this will be, in fact, 0, right, which we just talked about, with, that it has 50% chance going to the left, 50% chance going to the right. Okay, now we're at p squared, right? This one, if we do this, psi n star, right? Momentum squared is just negative 8, so times negative h bar squared d squared by dx squared. Right? Just like in the Schrodinger equation, just you have the 2m here in the Schrodinger equation. Psi n dx. If you do this one, you get pi squared n squared h bar squared over a squared. Okay. Now, using our equations that we know sigma x, the standard deviation is root x squared, right, expectation value of x squared minus the expectation value of x squared, and then sigma p, we know, is root expectation value of p squared minus the expectation value of p squared, right? And if we sort of skip some of these steps and just go find what sigma x, sigma p is, right? If we do this, it is the square root of n squared pi squared over 12 n squared pi squared over 12 minus 1/2 inside the square root all times h bar, right? And as you can see, the least uncertainty, right, the least sigma x, sigma p product, right, you'll see this thing will get bigger as n increases, right? As n gets bigger, the inside of the square root gets bigger, right? And so the smallest is n equals 1, and at n equals 1, the uncertainty, sigma x, sigma p, is approximately, let's see, it's 0.568 h bar, which is greater than or equal to h bar over 2. right? So the every state then has a larger sigma x sigma p, so it will definitely be greater than or equal to h bar over 2. So all these states do follow the uncertainty principle. Now, the important thing I do want you to keep in mind here is this pi squared n squared h bar squared over a squared, right? And you will see why I would like you to pay attention to that one, because it seems very similar if we just have that 2m down there to the energy, which would make sense, and maybe you can figure out why. I'll have a little bit more on that later in this video. Now, given this, I do want to do one thing before we go on to our problem, which is I want to just remind us, because I showed this a few in the simulation, but I want to draw it by hand just to show you what the solutions look like, and I'm drawing our potential here. So I'm going to draw each solution. I'll try drawing them in different colors. We have this is our n equals 1. I'll write just a code, n equals 1 here, right? Our n equals 2 solution going to look like this. Now these are the wave functions, right? And so they will, when we take the square of them, it will be positive, right, when we have the probability. So this is n equals 2. N equals 3, let's do in red. Let's see if I'm not a phenomenal artist on this. So n equals 3. I think you get the point. The n equals 4 will go like that and then back down, right? So the number of bumps it has actually corresponds to its n. And we'll have more on that with what is called the node theorem a little bit later. Okay. And hopefully this makes sense, right? With our x squared and especially our expectation value of x, right? And how this one, right, the one that looks more like the Gaussian, looks like it probably has the least amount of uncertainty, right? Okay, so I'm going to get rid of all this, and I have a problem for us to solve. And this is a quite interesting problem and very important to make sure you really understand what's going on here. And we'll have a few maybe kind of new concepts introduced here, right? And so this is with what is called an initial state wave function, where I am going to give you the wave function psi at time equals 0. So psi of x and 0, right? And this wave function, in this case, will be a x times quantity a minus x. Right? And if you graph this, what it will look like is it will look kind of like our initial state, or n equals 1 state, will look like that. It's a upside down parabola, and again, this is only between 0 and a. Right? And so, right, so this is our initial state wave function. You may think that it would look a lot like, have very similar properties to our n equals 1 wave function, which it in fact does, because it does obviously look a lot like it, so it will probably have some similar properties. But the first thing we need to do, of course, is normalize this, right? And so let's write out what our integral is. Well, we want the integral from 0 to a of norm squared of psi x 0 squared dx. Right? And if we do this, we will get, and again, this is like the integrals that I have done, and I'll just use them. We're going to get a squared, it would really be the absolute value of a squared, times little a to the 5th over 30. Right? And this, we know, does have to equal 1. That's our normalization condition. So given that, we can see that a will be the square root of 30 over a to the 5th. Right? And so let's just put that back into our wave function here. right? That's going to be our first step always, is making sure it's normalized. So this is 30 over little a to the 5th. Hopefully you can read that 5. I'll try to make it a little bit better. I'll squeeze it in there. That's not even better. There we go. Okay, so I'm going to erase this now, right? And now I want to know, say I ask you, I want to know what the probability of having the energy n is, or the energy level n, right? And I don't even have to give you a specific one. We can just solve for this probability in terms of n. And how do we do this, right? Well, we will get, we want Cn, right? Because then we take its norm squared. So first, let's find Cn. Well, we know how to construct Cn, right? This was our probability postulate, if you remember from a while ago, and we've done this more since, but with the inner products, right? We know that this, and hopefully you remember this. If not, go review section 2. This is the inner product of psi n, right? The wave function with a definite energy. This would be like our phi sub e. Inner product with our wave function, right? And we don't even need, right now, actually what we'll be doing, and you'll see why, is we'll be actually figuring out how to express our wave function as a function of time. But think about conservation of energy. The energy makeup of our wave function, right? The probability of having a certain energy is not going to change over time. It can't. That would violate the principle of conservation of energy. And if you think about that video that I think I recorded, was probably 4.3c, with the with finding the expectation value of energy, what you can see is the expectation value of energy, right? If you look at that, will have to be time independent, right? We didn't ignore the time part in that derivation, and we found the expectation value of energy is time independent. It will be the same, right? Which makes physical sense, right? So if we find Cn for psi of x and 0, we find it for all time. So x and 0, right? And if we do this, well, this is the integral from 0 to a. I'll write it down fast. Root 2 over a. We don't need to take a complex conjugate here, right? Because all we need is this, the function of x right now. So root 2 over a sine n pi over a x. And then times our wave function, so root 30 over a to the 5th x minus a dx. Okay, and if you do this integral, what we will get is 4 root 15 over, there's one more part, times 1 minus cosine pi, or cosine of n pi, over pi cubed n cubed, right? But what I want to point out is that this 1 minus cosine of n pi, if n is even, right? If n is even, right, then cosine of n pi, right, if it's 0 or 2 pi or 4 pi, is going to be 1, right? And 1 minus 1, this will be 0. N odd, right? So apparently it can't, this wave function, if we have in this initial state, can't have an energy with a value of n that's 2, 4, 6, 8, any even number. N odd, right, cosine of pi or cosine of 3 pi, that's negative 1. 1 minus negative 1, that's 2, right? And so now we can just write this as, right, 2 times 4 root 15, so 8 root 15 over pi cubed n cubed for n is odd, right? And this is our coefficient with the energy, right? And now we can, first thing, write out our general wave function, right? Because we know in general, psi of x and t, and this is something, we sort of did this and you didn't even realize we were doing this, right? Psi of x and t in general, we know, is a sum over all possible values of n, right? All possible values of n of Cn, Cn psi n e to the minus I omega nt. And I can actually write out what that energy would be, or what E sub n is. We know E sub n is n squared, or yeah, let's see, how did we have it before? I wrote it out as pi squared n squared h bar squared over 2m a squared t, right? And we know what c sub n is. So in general, our psi of x and t, right, is summing over all possible n, but that's just n is odd, right? Cn is 8 root 15 over pi cubed n cubed. And then we have our root 2 over a that we cannot forget about, right? We still have to make sure, right, these psi sub n's are normalized. That's the only way this solution will end up being normalized, right? But again, if it's normalized at one point in time, it's normalized at all points in time, right? Sine n pi over a x e to the minus I pi squared n squared h bar squared t over 2ma squared. I know it's a little bit messy, but you heard me say it, so hopefully you can kind of get this. And that, right, maybe you should be a little bit impressed, actually, right? Because we were just given an initial state wave function, and we just used our postulate, right, our probability postulate, and we were able to construct, right, just given the initial state, and knowing what the solutions, the time-independent solutions to the Schrodinger equation is, we were able to find the time evolution, right? This equation shows how our function evolves in time, right? And if you plug in t equals 0 and do this sum, which is not a super pleasant sum to do, although if you are familiar with sort of the tricks of partial differential equations, you may know how to do this, you will in fact get this quadratic back, right? Which is pretty cool. So this does work if you plug in t equals 0, right? And so we found our general form of the wave function, but I want to go back to the question I initially asked. What is the probability, right? I want to know the probability of having an energy E sub n if I start in this state. Remember, this probability won't change in time. These coefficients don't change in time, right? Even if you plug in the time part for it, right? There's no time part in here. So, but these coefficients will not change in time. If you do this integral for this wave function, that's a function of time, it won't matter. I know you're probably sick of me saying it, but you can watch that other video where I show, right, the equation for the energy, for the the expectation value of energy won't depend on time, and hopefully you can see that the energy of the superposition won't depend on time, right? That would make sense. Or the energy makeup. Okay, so P of E sub n, well, that's just Cn norm squared, right? Well, this is not complex, so we can just write this out. 8 squared is 64 times 15 is 960, so this gives us 960 over pi to the 6th n to the 6th. And just to show you that the solution that we have right here is very, very close to the n equals 1 state, let's just see what's the probability that our function has e sub 1, right? And I plug this in to this equation, and I got 0.9986, which means if you measure the energy of a particle that started in the state, it will have a 99.86% chance of having that first energy, right? Which will show you because this state is obviously very close. Now, one other interesting thing that this gives us, and I really don't want to erase our general solution, so make sure you have that written down, but I have to erase it for some space. Right? Another cool thing this tells us, right, which you can confirm, and this is just a really cool fact of math, is we know, right, that the sum over all possible n, right, in this case it would be n odd only, because all the other cn's are 0, of cn norm squared equals 1, right? And so given this, we know that the sum of, for all odd integers, of 960 over pi to the 6th n to the 6th is equal to 1, right? Or another way to write this is the sum over odd integers of 1 over n to the 6th. So that's 1 over 1 to the 6th plus 1 over 3 to the 6th plus 1 over 5 to the 6th, on and on. This is equal to, right, on and on to infinity, this is equal to pi to the 6th over 960, which is just a pretty cool mathematical result. Okay, so now a few last things to do, so I'm going to erase this. Hopefully you have it written down. I want to check the uncertainty principle just for the initial energy state. Right, actually, I think I have one other thing to do after this. I want to check the uncertainty principle for this initial energy state. Right, I'm not going to write down what integrals I do. I'm just going to let you know if I plug it into this initial energy state, the expectation value of position at time equals 0. Right, that's how I'll write it. Time equals 0. It's of 0. Right. Actually, I'll write of t equals 0 is a over 2, which makes sense, right? If the expectation of the position is right in the middle. The expectation value of position squared at t equals 0 is 2a squared over 7. Right? If you just do these integrals, expectation value of momentum at t equals 0 will be 0, right? And I want to note these quantities can, I'll write this, these can change over time, right? And they will change. This wave function will evolve in time, and the expectation value position squared, and momentum will change over time. Interestingly, momentum squared at t equals 0 is going to give us 10 h bar squared over a squared, right? And so this will give us 10 h bar squared over a squared. And it turns out that this, even though it's at time equals 0, momentum squared, in this case, will not change in time. And I will show you why very shortly. First thing, if you just do our sigma x, sigma p, right, sigma x, sigma p, all at t equals 0, what you'll get is you will get root 10 over 28 h bar, which is about 0.598 h bar, which is, of course, greater than or equal to h bar over 2. So it works, and it turns out throughout time it will work as well. The uncertainty principle will never be violated at any point in time, even though the uncertainty could change in time. Now, p squared, the expectation value, and this is the very last thing we will do, it does not change in time. And I want you to think about this. we know that the energy of this particle, it has no potential energy, so the energy is only kinetic energy, right? It's only kinetic energy, T, which, capital T, which is p squared over 2m, right? So if you think about it, the expectation value of energy would be the expectation value of p squared over 2m. But mass is a constant, right? So this would just be the expectation value of p squared over 2m, right? And the energy does not change in time. It can't, right? The expectation value of energy, that's the conservation of energy. And we'll get more, like in section 5, we'll talk very, very specifically about how observable quantities will change in time, how these expectation values will change in time, right? But the expectation value of momentum squared, since it's proportional to the expectation value of energy, it can't change in time, right? And if you look at this, and if you compute the expectation value of energy, either using the Hamiltonian operator or the energy operator with our other equation, either will work. It will give us 5 h bar squared over ma squared, which you may notice is exactly p squared over 2m. So you can get this with the integral independently, right? Just using the integral for the expectation value, which should make sense because the Hamiltonian operator, if you use the Hamiltonian operator, did the integral of psi star Hamiltonian operator acting on psi, right? The Hamiltonian operator is proportional to the momentum operator because potential energy is 0, right? So if you do it, if you write down the two integrals, right, psi, minus h bar squared d by dx over 2m, right? This is the Hamiltonian, right? Right, and for momentum, it's the integral of psi star negative h bar squared d squared by dx squared, psi dx, right? So it would make sense that these answers will be off by a factor of 1 over 2m, right? Okay, so with the integrals that works. Hopefully, again, if some of this doesn't make sense, go rewind it, watch again. This is really important stuff for quantum mechanics, how to construct a wave function, how to show, right? What we showed is we got an initial wave function, we used the Schrodinger equation. The idea, we solve the Schrodinger equation, we use these solutions to determine, using our coefficient equation with the probability postulate, the inner product. We use our Schrodinger equation solutions to tell us how this function evolves in time, right? Which is really what the Schrodinger equation does for us. And then we did some other things with those solutions, and hopefully you understand the infinite square well very well.